All right, so if we want to be able to talk about the momentum in the x direction, initially and finally, we want to make sure that we're only considering the momenta in the x direction. It would be really a very common mistake to start plugging in, all right, here's our velocity, it's 5 meters per second. Here's our mass, it's 60 grams or 0.06 kilograms, right? Let's just plug that in and start blasting away. But that wouldn't be correct because the total momentum here isn't going to be a conserved quantity. We can get useful information, like we said in the previous video, that that the momentum in the y direction is going to be conserved because there's no external forces along that direction. So we just want to consider the change in momenta along the x direction, because that change in momentum along the x direction is going to be equal to the average force times the change in time, right? This comes from the fact that this could be about the integral of the force times dt is equal to the change in momentum, but the problem specifically asks for the average force, right? So the average of force is asking us to figure out, all right, well, we don't know exactly how this force changes with time, but since we just want to know about the average force, that's assuming, even if it is changing rapidly, even if our force with respect to time does look kind of crazy and is something like, increases like this and then goes down, it's specifically asking us for just an average value. So whatever that value is, let's figure out what that is. That's for some large interval of time from some initial to some final time. And in this case, that's equal to 2 milliseconds. Oops, that's not on the board. So that's that force versus time graph. Okay, so we're just asked about the average velocity. That's why we're considering just the change in time that they give us. All right. So the change in momenta in the x direction, we take the final momentum. Let's make positive x be to the right. All right. So positive x is going to be to the right. So the final momentum in the x direction is this pf sub x, and it has a vector. Well, it's to the left, right? So let's actually just call that negative because it is to the left. All right, negative pfx to the left. We'll leave the vectors off because we're only considering the momentum in the x direction. We then subtract the initial momenta, which is pix, to the right, so that has a positive sign. This minus comes from pf minus pi. And we plug in the value of pfx, that's a negative value, and the initial pix, that's a positive value, so this minus sign stays put. All right? And that's equal to the average force times this change in time. The x component of the final momenta is minus its mass, which is 0. Well, let's just put this, the mass times the x component of its initial velocity minus the mass times the x component of its final velocity, right? And now we're going to be considering the magnitudes of these. We've already considered the direction once, so we want to make sure that we're just looking at the magnitudes of those values. And that's going to be equal to the average force times the change in time, all right? Now, it's really at this point just a question of plugging in and making sure that we get the right components. You can see maybe by our picture a little bit what angle do we need to consider if we just want this x component of this velocity. This is something from geometry maybe some of you remember. It's called a zangle, right, where you have this line here and this line are parallel to one another. So the angle inside here equals the angles inside. It's kind of like a big Z. So this is going to be 40 degrees also. And that lets us know that we need to use cosine. So minus m times the, oh shoot, I flipped these around. I'm not sure if you can see that. Alright, sorry. These are flipped around. This should be the final, and this should be the initial. Just simply mislabeled those. Sorry about that. So the final x is, we're now just looking at the magnitude of that, so that is our final velocity, which is 5 meters per second, times cosine of theta, which is 40 degrees, minus m times 5 meters per second times cosine of 40 degrees, equal to the average force times our change in time, which is 2 times 10 to the negative third seconds. Sorry, our mass, we could have plugged that in as well. If you can look here, this quantity and this quantity, the magnitudes of those are actually equal to one another, right? So this whole thing really just becomes negative 2 times m. So that would be negative whatever the cosine of 40 degrees is. I'm not exactly sure what that value is. So this would be 2 times 0.06, so that would be 0.12 kilograms times 5.0 meters per second times cosine of 40 degrees divided by 2 times 10 to the negative third seconds, and that all of that would equal the average force, right? And what does that tell us? I should have been putting these vectors in a little bit, right? This is the average force. We know that this average force is going to be acting, all this was in the x, so we know this is the average force in the x direction is going to be a negative value, right? And that should make sense because we chose positive x to be to the right. So if positive x is to the right, the average force by the wall on the ball should be to the left, right? Because the ball is coming in and then its momentum in the x direction is changing due to the force exerted on this wall over this time, by the wall onto the ball over that time interval, right? So we get some value for the average force, and I don't have my calculator with me, but it would be pretty simple to plug all of this stuff in and get an answer. And we could even look to make sure, look at our units real quickly. Here's kilograms, meters per second, and dividing by another second, that'll give us kilogram meters per second squared, which is a force, right? So that's excellent, that's newtons. So whatever the value of that is, we could figure that out, and that's how we would do 8.47.